At Service Logic, we believe the future of the skilled trades lies in training and development. And that's why we created The Edge, a platform dedicated to empowering our greatest assets, our people. From hands-on training to leadership development, Edge is where technicians grow their skills, expand their opportunities, and build lasting careers. Because when people succeed, our companies, our customers, and our industry thrive. This is The Edge. This is the future of the skilled trades.
I chose iConnect training equipment because I already previously had some iConnect training equipment. And I was very pleased with the equipment I had, the quality of it, and pre-designed labs that came with it. So when I expanded it more into the catalog, I decided I wanted to get this refrigeration trainer in my program to expand my program. My experience so far using the TU-155 has been pretty good experience, especially my second year students, and the light bulb kind of syndrome goes off when you see that little flicker in their eye and oh, I got it. That's what us instructors, what we look for is the I got it moment. And this helps me to the I got it moment with my students, and that's what's my goal to achieve.
We are Daikin, the #1 global indoor comfort provider. Our innovative home and building solutions are engineered with energy efficiency and sustainability at their core, ensuring improved indoor air quality for all. From heating and cooling to ventilation, air purification, refrigeration technologies, and connected devices, we're at the forefront of technology, addressing the pressing challenges of sustainability.
Thank you all so much for joining us once again on Did You Know, the ESCO HVAC show. Boy, do we have a special treat for you today. Check this thing out. Yeah, we definitely want to thank our amazing sponsors for this show, Howard. Look at this thing. I'm telling you what, we're going to have such a good time today. We're spending some time with our good friends at Danfoss. We're going to be diving into their mobile CO₂ trainer. You know, we've been so excited here at ESCO about our new mobile studio. And when Danfoss wanted to introduce their mobile CO₂ trainer, I'm like, yeah, this is exactly what we're going to do. So they've got a video production crew. They got a variety of different angles for us to check out. And I want everyone to let us know in the chat where you're joining from. Love to see how large this community is growing. I just got back a few hours ago from Norman, Oklahoma. We were doing some technical training with one of our equipment manufacturers. Grateful to spend some time out there today. So guys, why don't you go ahead and introduce yourself today, and we'll talk a little bit about this CO₂ trainer and how Danfoss is helping move the industry forward with CO₂ refrigeration.
Thank you, Clifton. I want to say that we greatly appreciate you inviting us to do this, getting to spend time with you today and show off our Danfoss Mobile Training Unit. My name is Jeff Miller. I'm an application engineer with Danfoss. I've been in the industry for 22 years. I've spent 12 years in the industry doing service, install, EMS. I spent the last 11 years with Danfoss, and we're super excited to show you the MTU today. This is Dwayne. Dwayne has been with Danfoss for 9 years. He is also a project engineer, and he's going to demonstrate the MTU and be mobile around the unit and show you what we have on the rack.
Very cool. Yeah, this is going to be a combination of curriculum as well as showing some of the components, the actual live things, which we talk about here on the show all the time. It's very important for us to be able to grasp these new concepts with a combination of classroom curriculum as well as that hands-on experience. And Danfoss is really bringing that to you today. So we're grateful that you're hanging out with us.
Great to be here.
Where do we begin? Hey, Kendrick, thanks for joining us in Chicago. Paul Leonardi up there in South Jersey. All right, what do you think? Where we start?
Let's go ahead and start with the presentation.
Okay, let's do that. We'll hop on over.
Okay. So we want to introduce the Danfoss Mobile Training Unit, and we're going to have a focus on specifically the multi-ejector that's on it. So let's go ahead and get started. Just a few things to know about the MTU. It is completely portable. It's approximately 8,000 pounds. It is, like I said, a mobile trailer. It is a medium temp suction group with parallel compression. So we have 2 compressors on each with VFDs on each compressor. We have an evaporator, gas cooler, and all that involved. Some of the premise to why Danfoss put this MTU together was local hands-on training. This trailer gives us the ability to go around and get technicians hands-on with not just CO₂ technology as it is today, but also future technology as we amend it to the unit.
Yeah, we see CO₂ as a really expanding sector of not just the commercial refrigeration, but a lot of other aspects of our industry. As we continue this HFC phase down, we're really not left with a lot of alternatives. So we're really re-looking at our fundamental refrigerants like CO₂. It's a very important part of our educational future.
100% agree. One of the other things this gives us the ability to do is also get more people familiar, contractors, with the stuff that's on the rack. So that puts hands on without having to be in a grocery store and possibly causing downtime or anything like that for training.
Yeah, bringing the education where it's needed.
Yes. For the end users, for the customers, it gives us the ability to give proof of concept without necessarily have to do a test store. With our ejector technology on here and using parallel compression, we can walk customers through that without having to do a 6-month design phase, integrating all that and then waiting on results. They can see it and put hands on today.
So this will be the actual refrigeration equipment that we're going to be seeing in particularly scenarios like grocery stores and other refrigeration applications then?
That's correct. Yep.
Fantastic.
This is just an outside picture of what it looks like. And you see that behind me. Dwayne's going to give us a demo here in a minute. You can also see the P&ID loop. So you can see how it's all kind of piped in. I know that's a little small. There's a little bigger version of it.
There we go.
So you can see here we have the ejector technology. Yeah. We have IT compression, MT compressors. This whole rack is mainly Danfoss components. So everything on here is Danfoss. Yep.
Very nice.
This is just an overview of what it looked like before we stuffed it in a trailer and coated it and made it all nice and pretty.
Yeah, it's looking very familiar. I'm really liking the theme here. It's very similar to the trailer we put together, and it's so nice to be able to take the education on the road, and that's really what you're doing. You're bringing it to wherever the training is needed.
Yeah, that's one of the things with our previous unit. It wasn't quite portable, so we took that feedback back and decided to put in a trailer, and now we're completely portable.
Love it.
So now we're going to get into the Danfoss components that are on the rack. And again, this is just a touch on a few. Components that are on this rack, we have our BOC compressor, our VFD, our PL1 line, which are valves. So we have our ejector, CCMT, and all that stuff. Pressure switches, PL25 electronics controls. So, and then also the sensors, which is PL04. Yeah.
Very nice. Look at that.
Yep. Dwayne is going to give us an overview of our BOC compressors. As you can see there, we have our parallel compressors, our ITs are intermediate, and our MTs. And then we also have on our back, we have our CMT. valves and our VFDs. There's our VFDs for our compressors. We have a VFD on every compressor. Our CCMT valve, that does everything from high pressure to flash gas. And then we also have our ejector.
This is so exciting.
Yes. And like I said, this allows us to put technicians with hands-on. Yes.
Yeah, for real. Yeah, I mean, everything looks so familiar here. And that's one of the things that we like to teach the programs. As we move into things like CO2, we're still talking about a refrigeration system. We're just changing the refrigerant and sometimes a few of the application components. But as far as the actual circuit, it is just another refrigeration system. We have to get used to the things that are different because many times we already know the things that are the most common.
Right. Just to discuss some parts on these components.
Okay.
Our Danfoss bot compressor. Danfoss has got into the reciprocating compressor.
Mm-hmm.
So this compressor has a internal oil pump. It is VFD rated. We also have digital compressors in this, which is they call their flex CO2 control. We have these in transcritical, subcritical. Those are all available. The VFDs, the FC103s, those are designed to actually work with our front end controllers. So you can actually see what the compressor is doing as far as amp draw per phase, total amp draw, power factor. There's lots of data points you can get from it.
Very nice.
Our CCMT valve, this valve's amazing. It does like a multitude of different functions. It can function as a flash gas bypass, a high pressure valve, an expansion valve, or a suction regulator.
Oh, really? Just by programming?
So yes. So there's when we put this in, you can actually program the pack controller in order to, depending on the application. Yes. So it's
Very
basically
cool.
4 valves in one.
Yeah, that's what I was just sitting here thinking. That it's a lot of flexibility with that one component.
Yes. Yeah, it's a fantastic valve. It also does inventory reduction for OEMs and stuff like that. You know, sizing's different based on the application, but the valve can be used in a multitude of applications. Yeah.
Now, I'm sure a lot of people are familiar with things like a suction regulator, the expansion valve, maybe a high pressure regulator. Can you tell us a little bit about that flash gas bypass regulator application?
For sure. So the way it works is, in our control strategy, is that you want to keep your ratio from flash gas to liquid in your flash tank. You want to keep it to, you have room to bring liquid in.
Okay, so we're controlling volume.
Correct. So how do we keep that ratio? So the way we do it is we have to get rid of the vapor that's on that tank. So the way we do it is that valve opens, and it's a stepper valve. So it opens to allow gas to come out and then be pumped through either the IT if you have parallel compression, or if you're doing, you don't have parallel compression, you do it through your MT compressors.
Very cool. Okay. Well, I know that's one of the newer components with the CO2 system that not everyone may be familiar with.
Yes. Yep. So that's pretty much the CCMT. Like I said, it's got a multitude of applications it can be used for.
I like it.
The EKE superheat controller is another thing that we have. Currently on this rack, we use it for controlling the pressure on the evaporator. So we can, adjust the back pressure. Yep. Okay.
You bet.
The main thing on this rack that is really nice to show is the ejector. The current ejector that's on here is a Combi ejector. Okay. It actually has 3 cartridges that does high pressure. It has 1 cartridge that does liquid injection, and then it has 2 low pressure ejectors.
Really? Okay.
So what that does, it gives us the ability to demonstrate for a customer or show a contractor how we can switch it in different modes. And we can do that all with 1 ejector.
All right. So another universal part then is what you're applying to the design.
Correct. Yeah. And you can have a multitude of blocks,
Okay.
or you can, in this case, we have one block.
All right.
So to get in,
okay,
Yep,
I
go
see.
ahead.
There you go. No, I was getting ready to ask how you apply the different ejectors onto the block, but I think you're already there.
Yep, for sure. So on the left, you're going to see a standard booster system. So you have your LT compressors, your MT compressors, and all that's handling the load of the flash tank and the discharge from the LT compressors.
And so
Right.
LT for low temp, MT for medium temp.
That is correct.
Okay.
Then the next one you see, we're adding a parallel compressor, or IT. Okay. You can see there that the IT compressor is tagged into the flash tank. So that way we're actually using the IT compressor to actually take the vapor from the tank.
Oh, okay. Sure. Absolutely. And
So-
so is there
Yep.
just different design applications?
Yes. So with the parallel compressor, we get energy savings because your IT compressor is running at like a plus 36, and then
Okay.
your MT compressors are running at plus 18.
Oh.
So
okay.
by taking the flash gas to the IT compressor, we're actually saving energy by setting it to a 36-degree SST versus a plus 18.
Okay.
Yep.
Yeah, makes sense.
Okay. And then the next X application is we have a high pressure ejector. Okay. Now the way that high pressure ejector works is it's basically acting as a high pressure valve. It's causing the pressure drop. But what it's also doing is it's using the high pressure from the drop leg of the gas cooler to actually do a Venturi effect and pull the empty pressure through it and then mix it to the flash gas pressure and put it back in the flash tank.
Really?
Yes,
Okay.
that's where we get the energy savings.
Yeah, definitely.
Yep. And then in conjunction with the IT compressors, you get even additional more savings. So you still see the IT compressors in that layout.
Okay. Yeah, I am
The-
seeing that there. Okay.
Yeah. The last one that we see a lot of is a combi ejector. Now this one shows two different blocks. So the small block is a liquid, and then the high pressure is the larger block. Now the way this scenario works is it's very much the same way, except for we add an accumulator, because with the liquid ejector, we can do the adaptive liquid control. And what's going to happen is we're going to flood the MT coil. And because there may be a little bit of flood back, we use the accumulator to protect the compressors. But then what happens is we use the ejector to pull the liquid off the bottom of the accumulator, lift it up, so it's up to flash tank pressure, and then it goes in the flash tank. So therefore, we're using it to get more liquid out of the accumulator faster than waiting for it to boil off.
So these are 4 different design scenarios that we could see in the field. Are they by engineer spec or are they efficiency spec?
It's dependent on ambient condition. Yep.
Oh, okay.
Yep. So like we're here in Florida, so high pressure ejector would probably be more relevant here. So because the more transcritical we run, the more efficient the ejector becomes.
Oh, okay. That makes sense.
Okay. So with the HP and LE, or the high pressure and liquid ejector, that would be probably more for a season like might have half the year where it's in low ambient condition.
Yeah, Midwest
and
here, like
the
Indiana.
rest of the year high. Yep.
Okay. All right. So that's intriguing. So we can see the 4 different common designs. And so you're actually incorporating all 4 of these into your trainer?
Yes. So we can shift to any of these designs.
Very cool.
Yeah.
Well, I think that's where a lot of educators get hung up when we start looking at designs, because I've seen the different designs before, but I didn't really know what the actual application difference was. And so it really does come down to the ambient installation.
Yes. Yeah. It depends on the energy savings you want to get. You always, as Danfoss, we always want to optimize your savings.
Mhm.
So, it's just a matter where it works best.
All right. Very nice. And so you go over all 4 of those different applications in the training portion with this trailer?
Yes.
All right.
Yep. Just a little insight on how the multi-ejector works. You can see here that we take the high pressure, we use it to pull the low pressure through, and then you can see where it mixes, and then we through the diffuser, and then we have our flash tank pressure coming out.
Okay, so it's like it is an adjustable nozzle in essence.
Well, it's not necessarily adjustable. Each cartridge is sized for the application.
Okay. So it's got a particular capacity.
Yep. Correct. Yeah, and the ejector has a different capacity for each cartridge. So, and it is a step-up control. So if you have 125, the next one's 250. So it starts off at the 125, then 250, and if it needs 375, it'll add the 125. Yeah.
Okay, that makes sense now. Like I said, I'm learning myself. I've had very little experience with CO2. Now, I was a rack refrigeration guy, but that was with, CFC and HCFC and HFC refrigerants. So there's a lot to learn here. But when we look at the entire system, it's very similar, just a few additional components and adjustments.
Yeah. When I usually do training, I usually try to bring in the HFC aspect of it and what's different about a CO2 rack versus the HFC.
You bet.
Usually get into topics about the high pressure valve. I can usually deter them of, well, what's different from that from a holdback valve on a condenser? Mm-hmm. You have the same thing, same premise. Flash gas valve, I'll give you that. That's different.
Yeah, that's the one I typically see, and I go, it's
right.
We have another cylinder that we're working with refrigerant in it.
Right. So there are some slight differences. With a booster system where you have the LT discharge dumping in the back of an empty suction group, that's different. You don't typically see that a whole lot. So there are slight differences, but it's not too much more different. It's getting over the shock of pressure and a few minute additional valves.
So when we look at CO2 racks, are we commonly seeing a low temp compressor and a medium temp compressor in the same
Correct.
design application?
Yes.
Okay.
Yeah, we don't do that on the MTU, and that's strictly because of portability.
Sure. No, I get that.
To give you a little closer look at what internally it looks like. So here's a 6-valve injector. With the ejector here, you can see the high pressure comes in. The first 3 valves are off, and you can see the high pressure comes in, and there's little check valves that keep the first 3 from working that aren't engaged. And then the other 3 come on, and that high pressure gas moves fast through there and pulls the low pressure through. And then through the nozzle, it mixes. And of course, we lift that pressure, that empty pressure up. Mm-hmm. And then it's up to flash tank pressure. And then it goes out into the flash tank.
Oh, very cool.
And each one of these cartridges is a different capacity. So we can...
This multi-injector is really saving a lot of space because typically each of these would have been an individual component piped different directions, correct?
Yes. Yeah.
Okay.
It's only a 12 by 12 by like 2.5 inch block.
Yeah, I noticed it was pretty compact.
Yeah. Now, and of course that differs to application, depends on how much capacity you need.
Yeah.
You know what I mean? This fits a lot of applications. I haven't seen one lately that is more than 1 block.
Okay. Yeah, that's really cool. And so this is a new product then, because I've not seen anything like this in the industry.
I don't think this video is going to play, so I'm going to pass that one.
Sure, absolutely.
But here's the step up, like the different capacities and how it compounds the capacities to get to its 100% capacity. So you can see here it starts off at nothing. The next one starts at 125, then it goes to 250, adds the 250 with the 125. It's a linear gain.
Oh, okay. So with the one unit, you can increase capacity by stacking the units and running them almost in parallel.
So the way it works is the first cartridge that's in that block
Yeah,
will come on. That's number 2. That's your 125.
right.
And then like if I need to double that, I need more capacity, it brings on number 2. If I need, say, 375, it'll bring on 2 and 3. I'm sorry, not 2 and 3, 1 and 2.
Yep.
And then so on and so forth. And then until you get to the end where you have all of them on.
Yeah, that's very intriguing.
So it is, you can control capacity with it.
Yeah.
So you asked about how you choose, what ejector is right for you.
Right.
So 3 main factors: ambient temperature. Okay, that dictates where we're going to put it. The CO2 system type. If they're not going to do parallel compression, then we can't necessarily use high pressure.
Okay.
So that dictates a little bit. But plant type and system capacity also. So you can see it. You can also see in the high pressure, warm ambience. So here in Florida, prime example for that. But you do need parallel compression. Then also with the liquid ejector, you can do warm and cold climate. It doesn't necessarily need parallel compression, but it has to be all CO2 in a transcritical system.
And
So
that's a difficult one to get into and explain to people, is the critical transcritical side. Is there any easy explanations for that?
no, most of the stuff I see is transcritical.
Yeah, exactly. I've noticed by looking at the capacity chart for the refrigerant and the temperature operating, it's more actually looking at the chart. But that's what I'm seeing most of them now are in that transcritical design.
Yes. Yep. And that's something else that when we do a design, it's not like HFC bracks where you primarily looked at the warmest ambient condition. Now with CO2, you have to look at cold ambient and you have to look at the hottest ambient for design. And then you kind of aim for the middle, So it's not like before where we just aim for the hot. Yeah.
Exactly. Okay. A lot to learn here.
Yes. The combi ejector, it's just a combination of high pressure and the liquid ejector. So that's where in colder environments you could get that whole year round savings.
Yeah.
Yep. The low pressure ejector, I don't usually train on that a whole lot. It's made for smaller grocery stores.
It's limited on capacity, isn't it?
Yes. Yeah, tremendously. Yeah.
Okay.
So it's great for smaller stores.
Yeah.
Ideal in the application side on the medium to larger grocery. Yeah.
Okay. Very intriguing.
This is just another eyeball look at the ejector plate. So you can see here, this is like the one we have on our rack.
Okay.
The six ejector, and then the bottom one would be like a liquid ejector. So if you had them separate.
I would say that'd be a standalone then with just the liquid injection.
Yeah, if the customer opted just for liquid ejection, that's what we would do.
Okay.
To talk about the liquid ejector,
There we go.
here's a schematic of what just a liquid ejector would look like. You can see here there's no IT compressors, but we still have our accumulator, and we're using the liquid ejector to get the liquid off the accumulator, lift it up to flash tank pressure, and then put it in the flash tank. Is how that works.
Okay. I can see that now. Okay. And so is that more of an entry line design?
Say that one more time.
Is that more of a cost savings design?
It can be. Like I said, anything in the warmer climate, I usually would recommend the high pressure ejector.
Okay.
Especially down here where I'm at, I'm in Florida.
Yeah.
So that we run that quite a bit. But you know, Kentucky, Virginia, places where we get a little cooler, you know, we get a couple months of cool,
Mm-hmm.
then I would say definitely use a combination of both.
Okay.
So here is a full layout of what it looks like from a control standpoint too. So we have our PAC 782 that controls the rack itself. We have our SM880A that actually gives you a window into the PAC controller, so you can make setting changes and all that. We have our DGS leak detector. We have case controls controlling the EEVs. We also have our AKVP valves, and that PAC controller also controls our ejector plate, in this case our liquid ejector, and then also our CCMT valves. So you can see here again, we don't have any IT compressors because with the liquid ejector, we don't need them.
Okay. Sure. By design. Okay.
One thing with the liquid, one thing with the liquid ejector is it allows us also to do COM, which stands for CO₂ Adaptive Liquid Management. Now what that allows us to do, our case controllers run at stable superheat, MSS.
Right.
Now what this allows us to do is run adaptive liquid control. Basically what that allows us to do is to have our MT cases run with a flooded coil.
Oh, really?
Yes.
Okay.
So now the way it all kind of works is when there's a call for that and we're allowed to do it with the controls, it will flood the MT evaporator. But you know, there's always expectation you're going to have 1 to 3% flood back that may get back to the rack. That's why you have to have that accumulator. Okay. Now on the accumulator, there's optical sensors, and basically the liquid ejector takes the liquid off the bottom of the accumulator, and it basically gets it and, you know, like I said, mixes it and brings it in the flash tank. Now, if the liquid ejector is not capable of handling it all, there's a optical sensor in the the accumulator.
Accumulator.
And it will actually, if the liquid is not leaving the accumulator, it will actually take it out of adaptive liquid management. So and go back into stable superheat.
Absolutely. So we're using it for refrigerant management.
Yes.
So I've noticed, are we using any type of a receiver on the transcritical racks, or is it mainly managed on the evaporator and accumulator side?
So they don't use a receiver in CO₂. We use a flash tank.
That's what it's serving the same purpose as. Okay.
Yeah. We call it a flash tank versus a receiver because of the flash gas that's in it.
You bet.
Yep. Here's just another picture of how it looks like, a little more bigger view.
Mm-hmm.
This is the multi-ejector. Now we're going to get into the high pressure ejector. This is what we see a lot of currently right now from customers that they're using, is the high pressure. With the high pressure, if it's just by itself, you see there's no accumulator here.
Right.
It would normally, you know, be right here just on the MT side. Okay. So with that being said, the way the high pressure ejector works is it can work in place of the high pressure valve. Okay. It is causing the pressure drop instead of the high pressure valve.
Oh. Okay.
Okay. So, because typically you have, you know, anywhere between 725 to 1,400 pounds coming off your gas cooler.
Right.
Well, I can't put that in my flash tank. So we have to cause a pressure drop. Okay, so that's what the high pressure valve does. So, but in this case, the high pressure ejector can do the same thing. Okay, so, but where do we get the efficiency from the high pressure ejector? Well, the way we do it is we take that high pressure gas and we use it to pull through the low pressure MT vapor, and we use it to mix and then come out at flash tank pressure. So we're taking the mass load away from the MT compressors, putting it through the ejector, getting it to a pressure that can go in the flash tank. And that's where we're saving energy.
And
of
all that is being automated basically by temperature and flash tank level?
Yeah. Say that one more time, Clifton. Sorry.
So all of that is like the where we're directing the flow of refrigerant is really based on temperatures and level within the flash tank and how the controller is directing it into which compressor?
Correct. So
Okay.
with the flash tank, if our ratio of vapor to liquid is too much vapor, what'll happen typically, and this is if we don't have an ejector, okay, what'll happen is that CMT flash gas bypass valve will open.
Yep.
And typically it'll take some of the vapor and feed it into the MT side of the compressor.
Back into the medium temp. Sure.
Yes. That's how we alleviate that ratio if we have more vapor to liquid. So with this setup, instead of going to the MT, it would go to the IT compressors, which is that elevated that elevated SST, which is the plus 36. So that also gives you additional energy savings.
So are we constantly trying to balance that ratio between liquid and flash gas in that flash tank?
Absolutely.
Okay. I guess
Exactly
I hadn't
correct.
really understood that up to this point. That's
Yes.
making a lot of sense.
Yes. That's why we try to keep that flash tank at around anywhere between 34 and 36 degrees.
Okay.
Roughly around 520 pounds is what it needs to stay at.
Intriguing. Yeah, I haven't actually heard that. I mean, I know the purpose of it. I just hadn't realized that it was a ratio balance that we're actually attempting.
Yes, because if we're too much vapor, it doesn't do us any good. We can't cool just vapor.
Yeah.
We got to have that liquid.
Uh-huh.
Yep.
Okay. Yeah, thank you. I mean, that makes a whole lot of sense to me now.
No worries. Here's just another view, basic diagram. You can see the flash gas valve. You can see the IT compressors, the multi-ejector.
Mm-hmm.
And you can kind of see how, what I've already explained, that it takes the high pressure from the gas cooler, pulls the MT pressure through, mixes it, goes in the flash tank. If there's too much vapor, then it'll go to the IT compressors. And then it doesn't even use the flash gas valve during that process. So, and if the IT compressors aren't enough to keep that ratio down or that pressure in the flash tank, then the CCMT valve, that flash gas bypass, will open and start using some of the MT compressors to help.
I gotcha. Now it's making sense.
Yeah. In CO2, you'll find out there's a lot of redundancy.
Yeah, exactly. The ability to move refrigerant in based on its load, really.
Yes.
Okay. I can't wait to get my hands on one sitting at training.
We invite you to come on down.
I am definitely interested now because it's something I have to learn, and there's a lot going on. But when you start thinking about it, we're really doing the same thing. We're just managing refrigerant flow. But now, because we have flash gas as well as liquid in the flash tank, we can manage where to use it best.
Yes.
Which equates to efficiency.
Yeah.
Okay.
That last slide I showed you was in summer mode.
Yeah.
Which is with the ejector working, because this is a high pressure ejector.
Yep.
Now in the winter mode, the high pressure ejector isn't effective. So because we're in winter mode. Now it will still act as a high pressure valve, But what we're currently using is, instead of using the IT compressor, we're using the flash gas bypass in the MT compressors.
To maintain head pressure or high side pressure.
Right. So in winter mode, we go to a normal normal transbooster booster system.
Yep. I see
So
that.
I got a nasty echo.
Yeah. Yeah, I definitely see the benefit of that design, especially in a place like the Midwest where you have, cold and hot climates.
Yes. That's why, like in this scenario, if this was up in the Midwest, like you just said, then it would probably be a recommendation to use the high pressure and the liquid ejector.
Yeah,
So
absolutely.
you get year-round savings and not just summer.
Yep. Yeah, you get to enjoy the benefits in both climate.
Correct.
All right. I'm catching on.
Again,
It's taking me a minute, but I'm getting there.
Yeah, no worries. Again, this is just a repeat slide. We talked about this. This is the summer mode. It doesn't use the flash gas valve because we're using the IT compressors and the ejector. This just kind of shows you the mass flow and what's kind of going on during warm ambient conditions. So this one has the combi ejector on it. So you can see here we have our IT compressors, and they're running at 65%. It's taking a lot of the load of that flash gas.
Mm-hmm.
The medium temp side is only taking the 35% from the medium temp cases and the discharge from the LT compressors. So the ejector is taking the brunt of the load and making the flash gas pressure that actually goes in that.
Wow.
So you can see where we really take a lot of capacity away from the MT compressor.
Yeah, for sure.
So, and one thing that gives you the ability to do too in design is it gives us the ability, by adding the IT compressors, we can decrease the capacity of the MT compressors.
Yeah,
In a smaller compressor.
So we're going to see all three capacity compressors on this particular rack.
You won't see the LT, but there is the MT and the IT on here.
Okay.
Yes. Yeah, just because of portability and space, we left the low temp off.
But in this particular design out in the field, we would actually see compressors operating at three different
Correct.
Temperature
Yep.
ranges.
Yep, you got it.
Wow. I've not encountered that. So, okay. It makes sense, though, now that I can see it.
Yep. Here's just a breakdown of the combi ejector. Now, this isn't a representation of what's currently on the rack. We only have 3 high-pressure cartridges.
Sure.
1 liquid ejector and 2 low pressure.
Okay.
So, for demo purposes, of course.
Yeah, absolutely. Can't fit it all.
No. It's pretty much a playground now.
Yeah.
So, here's a breakdown of like the mass flow, like in a cold ambient condition with a combi ejector. This has the high pressure and the liquid ejection. So, in the cold here, we only have 17% of the flash gas load going to the MTs. We're not using the ITs because remember we're in cold ambient condition.
Lower temp, right?
Yep. And then we have 3% we're sending to the liquid ejector, and then the rest of it is going to the MT compressors. Yep.
It's very fascinating. Now I'm starting to see the energy efficiency gained. We're putting the refrigerant in its best used application.
Exactly.
Okay. Because that has been one of the concerns that we get from educators when they look at a CO2 system. And they go, well, there's a lot more components and we're moving things a lot of different directions. Not really. We're just moving when we have the ability to move refrigerant into locations where it's most efficiently used, we do.
Correct. Right.
That's all.
Yeah. If the IT compressors aren't going to be efficient, then we're going to use the MT. The MT is not efficient. We're going to move it to the IT.
Yeah.
Yep.
That's That's a very intriguing perspective. And hopefully that simplifies everyone's thought process when we start looking at the CO2 design. Because even in our own curriculum that we just released for educators for an introduction into CO2, we're going through the components and we're talking about how they're functioning. But when we look at the entire system design, now it helps me see that we're really just trying to allocate a refrigerant to its most useful compressor range.
You got it.
Okay.
So
Makes
here's
sense.
a warm temperature climate.
Mm-hmm.
So here we would be using the high pressure ejector.
Yeah.
So you can see here, it's got 132% of the mass load. You got 59% coming out of the flash tank. You only have 27% going to your MT compressors.
Mm-hmm.
73% is going to your IT. So
Yeah,
by
allowing you to
throwing
do
it
the
to the
work.
IT, you're going to that plus 36 SST instead of the plus 18 that the MT compressors are running.
So in all of the scenarios, our high side pressure is really maintaining very similar. We're just fluctuating how we're distributing the refrigerant to the vapor side.
Yes.
Huh.
How are we handling that flash gas?
Yeah, exactly. That's actually really good. I've been struggling with that, but this is making a lot more sense now. Thank you.
No worries. This one won't animate, but this is a pretty cool little graphic. It kind of has the animations that shows you how everything goes. Maybe I can send that to you, Clifton, and you might be able to post
overlay
it.
that. Yeah, absolutely. Let me see if I can. I'll work on seeing if I can grab that separate. And that's a restream function. That is nothing on Danfoss side. My restream is not good at playing animations or videos. We were struggling with that a while ago. I'll make sure that we get that overlaid into the edit so that can be seen.
Yeah, no worries. But again, it just shows the IT, the MT. Again, we don't have LT on the MTU, but in the field, you would see the LT.
Mm-hmm.
But you can see this is a pretty good representation of what's in the actual mobile training unit.
Okay.
So you have your liquid ejector and the high pressure ejector in that block.
Yeah, sure. So this is going to be a good visual of the trainer itself.
Correct.
Mm-hmm.
Now, we talked about energy savings.
Yes.
So how do we get some of that energy savings? So on this first graph here, this is standard parallel compression transcritical booster rack. Okay. The blue line is your MT suction group in capacity.
Mm-hmm.
The IT group is the red line. So you can see it tracks very linear, but we're using a lot of the MT compressor. Well, that defeats the purpose. We want to use as much as the IT as possible to get that energy savings.
Yeah, yeah.
Yep. So you can see in the next graph that we've added the combi ejector, and you can see where the medium temp tapered off on capacity, and we were able to boost the IT capacity. So now we're saving energy.
Now with the IT compressors, is that typically more compressors with smaller capacities?
They're usually sized pretty close to the MT compressors.
Okay.
The issue at hand is that it has to have enough capacity on the flash tank in order to run the ITs versus the MTs.
Oh, sure.
So if there's not enough load, it wants to throw it to the MTs, which of course is the lowest suction group, and we wanted to throw it to the higher suction group. So by using the ejector, we can increase that load a little bit on the plus 36, but decrease it on the plus 18.
You got it. Yep.
So that's
no
that
change
energy
in
savings.
compression ratio or anything on the compressors, though.
Say it one more time. Sorry.
On the IT compressors versus like the medium temp or the low temp, is there a change in compression ratio?
I don't think so.
Okay, that's what Yeah, because I mean they're all based on capacity.
Yeah, correct.
Okay.
Um, this next graph really shows the level of energy savings that you can estimate you would get. If you did just parallel compression, that blue line is just IT compressors. You're roughly saving 7-8%. We do have a program called IT Optimize that'll gain you another 3%, 4%. But when we add high pressure ejector to the two above, now we're up into the 18% range.
Wow.
So, but then when we add the high pressure in the liquid ejector, we can exceed that and get to the 23% range.
Yeah.
And again, that's all based on ambient condition.
Right. Yeah, it makes sense why we're going to that. I mean, you're saving a lot of work on the compressors.
Yeah. Let's talk about servicing the ejector.
Okay.
There's not much to it. Typically, it's got a built-in strainer. It's easy to service. Let's see if I think I got a picture of that. Yep.
Oh, okay.
So here's the strainer itself.
Right.
There's 4 bolts on top. It pulls straight out. There's a hex nut on the bottom, or a hex bolt. You literally undo that, pull the strainer off, clean it, but you also need to change the O-rings. That's the very important part.
Yeah, you bet.
And actually, the ejector has extra O-rings on top. So if you keep using those and replacing them, you'll always have them on site.
Oh, really?
Yes.
So your service O-rings are attached.
Yeah, it's hard to see in that picture, but there is 2 O-rings that sit on the very top of it, and those are extras.
Oh, very good.
Yes. So of course, very important to oil the O-rings.
Yeah.
You know,
yeah,
place them.
What's on top?
Yes. The next thing is is the actual coils on top. You know, just like any solenoid, you may have one go out. These are rated anywhere between 110 and 230 volt, anywhere between 50 and 60 hertz. We recommend to OEMs that if you're going to, the plug that goes on them, if it's lidded, that would be better. Just because then you know the solenoid's active.
Yeah, sure.
So that's always nice. So, you know, you might have to service that once in a while. I personally haven't run into that. Mainly I run into strainer.
Yeah.
One thing we also recommend is, you know, to run your system before you engage the ejector for a while, just to get all anything that's contaminants wise in the system.
Right.
To at least that strainer, clean it really good, then turn on your ejector. Yeah.
Yeah. No. Yeah, for sure. Makes sense. Nice. That's a lot of great information. All part of the class. How long is your class that you're providing with the hands-on portion?
I don't know right this second, but I'm sure our marketing team would, and it's on our website as well.
Yes, absolutely. Which I'm going to throw up a QR. I want everyone to go check out the mobile trainer, especially if you're interested in getting some hands-on training. Let's go check that out. Can we see some more of that trainer too? I'm really excited to see this thing.
Yeah, give us 1 second, Clifton. We'll give you another tour.
Now, we're so grateful that you're spending time with us today. You know, there's a lot of changes in our industry, a lot of new technologies, a lot of new refrigerants, and it's super important for us to stay on top of everything as we're making these changes. And so having that first-hand education from the manufacturers themselves is absolutely critical. Oh, look at that thing. That is a fantastic trainer. All right, there's our flash tank. Accumulator. And great camera work, guys. Very nice. Anyone have any questions while we're going through taking a look at this amazing trainer? Man, I love that. Yeah, it is a nice one, isn't it? So one of the things we'll want to learn is, how to make connections with Danfoss. I've got the danfoss.com site down there. Make sure to grab the QR that we have as well. Be looking for training out there. I know earlier we'd mentioned that the trainer is going to be in Southwest Florida for a while doing some training and then moving around. I'm trying to encourage them to come to the 2027 National HVACR Education Conference with it, get a little bit more hands-on instruction. So you definitely want to reach out and start making some contacts. This is the type of education that we all are going to need going forward.
We greatly appreciate the invite, Clifton. I hope to see you again soon.
Yeah, me as well. So if there's any final questions, anyone let us know in the chat. I hope you got a little bit better understanding of CO₂ systems. Now you have some resources for getting training on that. We look forward to future conversations with Danfoss, and I can't wait to get into one of the classes myself. All right, everyone, thank you so much for joining us once again. We're grateful that you're spending time with us, and we will see you all again next week on Did You Know? The ESCO HVAC Show. Bye, everybody.